This is the fish problem where we have a fish that's slightly more dense than water, and fish have to be slightly more dense than water, otherwise they're stuck on top. A friend of mine once caught a blowfish and it puffed up while it was on the deck of the boat and was full of air. When he threw it back in the water, it just bobbed along on top. Um, so we've got this fish. It's got a density of 1030 kilograms per cubic meter. Water is about 1,000 kilograms per cubic meter. And one of the ways it keeps from slowly sinking is it has an air bladder that it can expand with air and contract. And so air has a much less dense, 1.2 kilos per cubic meter. And so the buoyant force then cancels out the weight. And this happens when the density of the fish times its volume, which is a fish mass, plus the density of the air times the air volume, which this then is really just the total mass of the fish, right? You can become neutrally buoyant when your total mass equals the density of water times your total volume. All right, and so all we're after is this relationship, rho fish V plus rho air U equals rho water onto V plus U. And we don't know U and we don't know U V, but we can solve for this ratio, right? I can divide through by V and I get rho fish plus rho air U over V plus rho water onto 1 plus U over V. So I don't know U and I don't know V, but I do know U over V. And so I can calculate what U over V is. And I call that alpha. And if what we're asked for is what's the ratio of the volume of the fish to the total volume it has to increase to, right? Or what's the ratio, the increase, assume the volume of V, right? So we're after by how much, what fraction must the volume increase? And that's just U over U plus V. And so in terms of alpha, um, that's you can get there by factoring a V out of the numerator. That gives you U over V plus 1. So alpha over 1 plus alpha gets us to this ratio that we're after. And that's it for this little problem.